Welcome to Temple of Pwn, Part 5. Today we're going to be talking about some shell coding and Seccomp avoidance. And if you don't know what Seccomp is, I'll go to a little bit about it, and then you'll know for the future. So, shellcode. For shellcode, your understanding and knowledge of assembly is kind of required, whether it be x86, x64, ARM, MIPS, some custom like Pegasus or something. Just a wide range of stuff. Shellcode allows you to run or do anything on the system if you can actually get it to run, and that's kind of where the difficult part comes, is that you actually need something, executable memory where your shellcode lives to be able to actually run shellcode. So there's a couple ways to get executable memory. Having a no NX or dep bit, which I'm not really sure if I should say bit or just protection. This kind of allows for stack execution, so it makes a stack executable. So a lot of times with buffer overflows, if you're able to just put your shellcode on the stack and then just return to ESP or RSP, it'll just jump straight to your shellcode. You can also do a function call to memprotect or a system call to its related system call number, which I don't know off the top of my head. And this allows for a region to be reset with different permissions, and it's just kind of handy if you know where you're at in memory with your shellcode and just want to be able to make that certain area executable. And then mmap also can create a new memory chunk or load in a file that's executable. But most of the problems with mmap is that you don't have full control of where it's actually going to load. I guess you could specify a chunk that could be loaded, but then you start to load your shellcode into that memory chunk after because it's not owned by you yet. Most of the time. Mmap is kind of a pretty nifty function, but we're not going to look into it too much. So kind of what Seccomp is. Seccomp stands for Secure Computing Mode, and this is what prevents, it kind of just stands for Secure Computing Mode, but it stops and prevents specified system calls from being executed by the process. And this is useful if like you're in a Docker container or something. You don't want them to run system or certain kind of system calls that can escape from the Docker environment. That's where Seccomp will come in handy. It's used in that kind of sense of virtualization and kind of limiting what a user should be able to do on a system level versus just a user scope level. It's useful to avoid unwanted system calls and limits ROP and shellcoding attempts. It's, like pretty much just said, can follow into children or forking processes, and so it means if you're able to actually get some kind of execution and create a new process, there's a good chance that Seccomp filters will follow into that process if you're able to, and then it could still limit your ability to actually do anything. So we get into a whitelist versus blacklist approach. As with many protection systems, there are blacklist and whitelist approaches. Should the user be able to so the kind of difference is, should the user only be able to execute a certain system calls, so whitelist, or should they be allowed to execute certain system calls, or should they not be allowed to execute certain system calls, blacklist. So should a user should only be able to open a file, read and write from it, so that'd be like a whitelist, or a blacklist that we say should a user not be able to run exec VE, and that's it. They can run anything else. So that's kind of where we'll look at where we can try and avoid a whitelist versus blacklist approach. And usually whitelist is the best option, but it could also be the hardest to set up. So in the example I gave earlier where you have open, read, and write, your program itself might need different system calls to be able to actually function normally. And maybe your program itself is insecure in the sense that it needs more access than it actually should need, and that can cause problems in the future. That's all I got for slides. So hop in. In the Temple of Pwn channel earlier this week, I tossed in this a.out file, and we are going to look at it in Ghidra and IDA probably. Let's copy, make sure I don't have anything on my desktop with that file name. Nope. Don't worry about any of those pictures, or don't look too much into them. Otherwise you'll be pleasantly happy with my different Zoom backgrounds I use for classes. So I'll copy a.out out to desktop, open up an IDA first to see what it's actually doing. So we kind of, if we wanted to, we could run it to see what it's doing, but here we can also just kind of look through it. So it puts a string, how difficult it should be, reads in a number, and then compares the number to 1 539 hex, which is going to be 1337. It should also compare it to 0, which is doing right here. So this is going to be no Seccomp filter applied. 1, it's going to say, it says exec VE will be blocked. If it's 2, I guess if it's anything else besides 1337, it's going to be exec VE at, open, and open at are all blocked. And then at 1337 says only you know what you're capable of. And at this point, I don't even know if 1337 is even possible with the current program, but we'll get into that a little bit later. So next, I think I missed a little bit, and it's right here, this function called setup. We can look through it and we can see that there's some socket setups and binding. And if we want to look to see what port it's doing, we can see that it's connecting to port 8096, and that's where it's setting up for. And later on, we'll see that it's actually waiting for an accept call to that port. And then if it does, it's going to fork, and if it's the parent, it just keeps doing this loop, and if it's the child, it'll actually go into the main program, and that's where we're going to kind of stay at for our exploitation. So here it's going to compare our var24, which was actually, we'll rename that to difficulty, because that's what we're comparing to the 1337 again. This is just a little switch case. That's our switch or if statement, kind of looks like that was in there. And this just sets an easy filter, a difficult filter, no filter, and then a good luck filter. So if we step into the easy filter, we get a bunch of garbage. And if you were to look at any of the others, I assume they look the exact same. This is kind of just how, this part right here is just kind of how Seccomp is set up. There's actually some cool papers and research about it. It's kind of like its own programming language in a way. And I'll show you an easy way to read it, because I think the first time I found out or saw this, I was really confused, and it took me like an hour just to understand what it was blocking or what it was allowing. But what it does is kind of just sets up a Seccomp object, and then it will make sure that it actually is set. And then I think option 16 is actually to make sure that it follows into forks or children. So that's kind of where that part is happening. Looks like it's going to print test for some kind of debug reason that probably shouldn't be in there, but doesn't matter. And then it just exits out. So we don't really need to worry too much, but we'll go through all three, or we'll try to go through the no filters, the easy filter, and the difficult filter today, but we'll see how that works out. But anyways, we'll see that it prints out as connected. It'll read at 0x38, which is 4856 characters, off by 16. Read in 64 characters from our connection into this buffer, which if we look, we can see the buffer's at location 0x20, so we have a blatant overflow right there. And then it stream compares it to the word done, and if it's done, it looks like it just exits. If not, it prints received message and then goes back up to the read again and just does an infinite loop right here. But we got to remember that it's not going to keep appending to the buffer, it's just going to keep writing to the same spot. So if we overwrite it once and we go through and we want to overwrite it again, we can. Another thing we should notice is that there's no way for us to get data through our connection. It never actually prints data back to us. This will all be on the server side, which in a typical case we won't have connection to. So we just need to keep track of that later on. So we can try this out and see how it actually works, but we should have a good understanding. So we can just connect to localhost at 8096, and we can see that it prints out connected. So now if we type out a message, we can see that it also prints out message received. If we wanted to get fancy, we could maybe check to see if there's a client's or server-side format string exploit. But if we look through, we should see that it's just doing a %s on our data, and there's not really a good way for us to actually get anything. If we were able to read the server side, we may be able to get a leak like this. It's obviously printing some kind of data that was already on the stack, but we can't really go anywhere with that. So, as usual, we kind of just want to, get, let's do live.py, get a script going so we can actually get a good interaction with it and maybe see if we can get anything further. So from pwn, import everything. We'll do a p equals remote at localhost 8096. And at the end, we'll do a p.interactive just to make sure it doesn't die on us if we were to want it to wait or anything. Then from here we can kind of just test to see what kind of overflow we have. Or actually first we should probably do a quick check sec to see what the permissions are on the binary. And we can see that there's no NX bit, pi is also disabled, and it has read, write, execute segments, which is going to be the NX bit, and there's no canary. So with that kind of approach, we kind of just want to think if we can get shellcode onto the stack, then we can just go straight to it if we have a good gadget or something like that, which we can use wrapper for. Wrapper at a.out. Usually we want to check first to see if there's something like this, a jump RSP, which is exactly what we want. Maybe jump RAX would work if RAX pointed to our stack or something. There might also be a jump of equal, doesn't look like there's any good there. Call RAX could work if you're pointing maybe a little bit after the stack, or if you're really lucky and the return value pushed back onto the stack is valid shellcode. It doesn't really look like there's anything else, but there's sometimes also push RDI return or push something return, which could also help us there, but it doesn't look like we'll get anything. So actually I didn't want to close that just yet, but we'll have to look back up later. I gotta look it back up so I can save it actually. Sometimes exploitation just involves doing stupid stuff and then going back and doing it again. So we'll just save that. We'll call it jump RSP, call it that. Now we can exit out of this page. And that should be the same every time because ASLR is off on the, or pi is off on the program. So what we actually want to do is, since we have access to the program itself, we can actually debug it sort of. So if we just open it up with GDB, we're actually able to walk through it and see where it's at and see how the binary itself works. So if we actually set a breakpoint at this jump, and then we did, actually we don't want to set the breakpoint just yet, we just want to see where we actually crash. So let's do a p.sendLine of the word done. I don't think that new line or no bytes matter because it's going to do a string end compare with 4 characters, so it's only checking for these 4 characters. So we can just do done, and then we can do the letter. I think we should do a cyclic, but I can't remember the syntax. So cyclic of 58 minus 4 should be 54. Was it 58? No, it should be 56. Yeah. Minus 4, so 52. That should be all the buffer that's being read. If we wanted, we could have just spammed it, but I think this is a more delicate approach. So if you've ever used GDB with something that forks, you might notice that it says something like this. Or if we run it, set the difficulty to 0. Connect to it, Python live. See that it says no Seccomp vector applied. Detaching after fork from child process connected. But that kind of means we're still in the parent context, and it should have crashed, which on our side I think it did. I just don't think I programmed it well enough to report back saying end of buffer. But the way, yep, see right here. So since we're still in the accept, that means we're still in the parent focus. So if the way you set GDB to follow the child focus is say set follow fork mode child. And now when we, after this accept, which I can walk through it, do that. So now we're right after the accept, we can do next, just check to see if it's connected, and then here's the fork, which we next, and then we can see that it says attaching after process fork to the child process, and it just kind of sets your breakpoints and get out of here. Oh no. How did I do that? There, I guess I got rid of it. Alright, but it attaches to the child process, and now we can actually step through it in that context. And if we wanted, we could step through it just to the read, which here's going to do the filter. Nope, no filter because we put 0. Prints connected. Comes down to the read. Reads in our string, which if we look here, we can see it's on the stack, and here's RBP, so we have definitely overflown it. Get down the string compare, compares the done to our string, which it should be 0, which we can see. Keep walking, and now we get to this leaf, and we can see that at RSP, then we do $RSP, and we can get the string of JAA, and we can pretty much just kill this, but I wanted to reattach to the parent, which is a little difficult now because GDB technically is running the parent, but it's not in its context. So that's always fun. So I'm just going to quit GDB and probably p-kill all a.outs in case they've stayed alive on accident. And we'll run it this way and just connect GDB to it separately. That way it won't crash out if we detach from the parent. Attach to the parent, set the breakpoint, set the follow, and we should be good. So over here we can do cyclic dash lookup of our string, which was FAA. See that after 20 characters we have writability. Oh, that's where our RSP value is.
J.
Was it J?
Sure. Yeah, I think so.
Oh my gosh, I'll have to look quick. I thought it was F for sure. It's not even on that page. Gotta love it. Let's be down here anyways. You're right, it was J. Okay, so 36 characters. Thank you, Bailey. And if we also wanted to look, we could see that RSI points to the beginning of our buffer still. RBP is garbage because we own it. RSP points to pretty much nothing. Nothing else really looks good. That's a libc. Maybe that's no, it's string compare. It's libc address. That's just start. So we don't really control any registers besides what's on the stack at this point. Maybe RSI if you want to make the argument, but we might use that in our shellcode. No promises though. So we can get rid of this string and just put in a buffer of, let's see, we need done plus A's times 30, so 36 or 32 plus P64 of jump RSP. So now we can put our shellcode right here. But the problem we have is that if this was 36 characters after, this is going to be 42, and we're only allowed to write in 56, I believe. Yes. So that would mean we have 24 characters for shellcode, which we actually might be able to pull that off. So let's just see what kind of shellcode we can write up. I'm going to get a most shellcode on, there's a lot of places. I think Exploit DB has a lot of stuff. Usually just search bin sh shellcode. And, oh, shell storm. There we go. This is 32-bit, so it won't work for us in this current state. But this is 23 bytes. We need less than that. 28, x86. Let's go x64. There's a 24-byte you want here. But you can see that it's also pushing the the string bin sh onto the stack, or into RBX and then onto the stack. But what if, since RSI points to this string, what if we just put bin sh the characters right after and then just increment RSI by 4? Or in this case, we need to move it to RDI, but that should save us at least 8 to 12 bytes and make it pretty easy for us in this case. So we got bin sh, put some more A's in there, times 32 minus 8 for that string we just added will be 24. Feel like off by, nope, that should be right. But here I'll just go through a little, just some fun features that Pwn Tools also has for creating shellcode. Here we can pretty much just do any assembly we want. So RAX is already 0, so we don't need to zero it out. Our DI is equal to the done on the actual, the done it's comparing our string to. So that's actually in program space memory, which isn't writable at the moment. So we'll need to move RDI RSI. Actually, we'll do a LEA RDI RSI plus 4. So we can just get that addition operation and this move all at once. I'm not sure if this will actually save us bytes, but I think it should compared to add RDI4. So we need to make sure our DX is also 0 for this. Move our DX, our AX. And then we need to make sure our SI is also 0. And then if we move AL 59, I'm going to take a shot in the dark at, because I think that's exec VE, yep. And this is kind of where just the knowledge of the assembly architecture and just and instructions helps, because we know that our system call that we're about to call uses our DI, our SI, our DX for parameters. So we can do syscall, and I think if everything's right, that should get a shell. So I was hoping that GDB would have stopped right there, but it didn't. So we gotta actually get. Oh, I'm not running GB right now. Oh, that was the actual A.out. Darn it. That's why. Alright, I'm gonna have to wait a little bit for the program or the system to think that the binary is not connected to the port anymore, unless anyone has. Oh, there we go. I was gonna say unless anyone has a way to actually force it. It's like during testing, I just had to wait every time. Alright, NSH, go back to GDB, attach. I think this one did break, but I was just looking at the wrong page the whole time. So, Python there. Oh, why did we? So close. So.
Do you have to assemble the assembly that you ran?
That is a good point. That would be the problem. So let's reattach. Continue.
I was about to say, I'm
Yep.
like, that's freaking awesome if it does that.
Shellcode equals a symbol of shellcode, and then here you have to specify your arch, which is AMD 64. I think you need in string. Otherwise, you could do something like context arch equals AMD 64, and then automatically will do it for you. But I'm not going to do that, and I'll show you why in the future. Well, I guess not really. It doesn't really matter too much. I prefer to do it this way so I know exactly when I'm compiling if that's the error I'm having is based on maybe I did I386 instead. Okay, so there we. Nope, still not it. Am I off by 4? Is that our breakpoint? Nope. Where is our breakpoint on the stack? Is it in RBP? Yeah, right there. There's our breakpoint. So we're off by 4. That's not. Darn it, why'd I close GDB? Break. Set follow fork. So off by 4, which this should be 32, 36. Oh, yeah, because it was 36 from the cyclic, not 36 from the done. That makes sense. And the cyclic was after the done, so that should be 28. Okay, so here we're at our jump RSP. And if you wanted to make sure that our stack is executable still, it actually is. So if we step into RSP, we can load our DI, our string, move our DX, our AX, which will zero it out. Then move absolute string RCX. That doesn't look quite right. Which makes some sense if we were to have actually checked to see what our length of our shellcode is before actually attempting this. So let's do a quick just test. Shellcode. We'll just set this to off so it doesn't mess up our current GDB instance. 14 characters. So that might be a problem because we're currently sending in 4 more characters than last time. Which this is 36. 40, 48. Yeah, we're only left with 8 characters. So our shellcode doesn't actually work right here. So we'll need to do a little magic and actually put our shellcode before the buffer to actually get it to properly work in our context. So to do that, our shellcode, or not, our shellcode we can place right here, but we still need to jump to it, which we can do with just putting a jump instruction right here. And I'm not really sure on the best way to do this, but the way I kind of think it, the way I do it, I guess, would be, we know that we have 28 characters right here, so we'll probably switch the A to a NOP, and then do 28 minus the length of our shellcode. And then we'll add a shellcode, change this to jump, and then we'll just figure out what bytes we need. Maybe just guess. So it's 8. We can just say 28 from there. So we'll just do a NOP, copy it, and do it 28 times. So 2, just copy 2 of them. 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28. Then we can do jump top, assemble an x64, and all we need is this EBE2. Assuming everything worked out right. Jump is equal to backslash EB xe2. And we'll try it again. Oh, so we hit our NOP sled. Doesn't look like we were exactly right, but that's fine as long as we hit the NOP sled. Move RSI, RDI, RDI, RSI plus 4, sorry. And boom, we have exactly what we want for RDX, RSI, and then bin SH and RDI. So, moment of truth, we just continue. I guess we'll have to detach. And we can see that our shell doesn't work, and it's not going to work. In truth, it does actually work, so if we were to do touch, no, it definitely won't work. So the problem with that we're actually facing right now is because all of our connections previously were being done through accept buffer, or a different kind of file descriptor. And right now our bin sh is going to try and read from standard in and write to standard out and standard error, which we don't have access to on our side. So if we actually came over here into ls, I was thinking that maybe it would catch it, but I think the process itself kind of disowned itself from this terminal. I'm not really sure how that works, but we can check, and we can see that we have an sh running, just it's not really connected anywhere. But we could grab it in a different terminal, but it doesn't really matter because our exploit failed in that context. So now comes the approach of us trying to actually figure out how to bypass this or try to remediate from here. And there's a couple of ways we could do this. So since this is simulating a process or a service that's running, you don't know what file descriptor you're going to be. Usually it's just one less or one more than the previous one, which if this program was fresh would be file descriptor 3 or 4. But in our case, I kind of forgot how many times I've actually ran it, so we're out of luck in that scenario. And we also got to remember we only have 28 bytes of shellcode. So the usual method is called I think it's a socket reuse attack. And how we're going to do that is create shellcode to duplicate a socket, or not a socket, a file descriptor, and that will create a new file descriptor, just one more than our current one. So all we have to do is take the value from that, decrease it by 1, and that's our current file descriptor, and then we'll copy standard in, standard out, and standard error to that file descriptor, and then we'll run bin sh again, and we should have a working shell that time. So we'll save this shellcode for now, and we'll go to step 1. So do we want to... This shellcode that we're doing is definitely going to take more than 28 characters for sure, because it's there's kind of complicated steps, but you just have to realize that your 28 shellcode buffer isn't going to work. So do we want to bypass the buffer first, or do we want to write the shellcode to do the duplication first?
Shellcode.
Okay, shellcode to do the duplication first. It is. So if we look back at our system call table and we go up to right here, 32, we can see sysdup, and it takes unsigned int file descriptor. If you want, you could just do man dup to see what it does. And you can see it just creates a copy of an old file descriptor and then just uses the lowest numbered unused file descriptor for the new one. So if we were just to put 0 into our DI, call dup with it, boom, RAX now becomes the next value, decrease RAX, we now have the old one, or our current one. So we know RAX was 0 from where we were at with when we jumped to our shellcode. So let's use this for a quick reference to see what our registers look like. So let's move our DI RAX because our DI had garbage in it. Move AL32, syscall, decrement AL, and right there. Now RAX should have our current file descriptor in it. If you wanted to be more careful, actually you should probably do REAX, because that's 1 byte instruction, I'm pretty sure, versus minus AL, which is 2 bytes, or decrement AL, which is 2 bytes. So now we have our file descriptor we want. So at this point we could do something like just open and read a file and then send it to us, or what we're going to do is use the next dupe, which is dup2. And if you want to figure out what dup2 did, you could go to man again, dup2. And this one does, it creates a copy of a file descriptor from the old one to the new one. So if we put in standard in and then put our current file descriptor, it'll copy it there. Actually, no, right here. Dup3 does some flags. I don't know anything about the flags though. So we do 0, 1, and 2, and boom, we should have it. So we'll just need to make a quick loop. We'll put into RCX nothing because we won't want to use RCX, and I'll explain that a little bit. But usually RCX is kind of used as a counter for these kind of, or most loops. But if you use RCX when you use a system call, it's going to automatically overwrite it because RCX is set to the value that you should return to after a system call when it jumps to kernel mode. I don't know the exact specifications. I just know that RCX is not a safe buffer to use or a register to use with system calls in 64-bit mode. So we'll move our DX nothing because nothing's going to be guaranteed to be 0. I think RBX could be, but we're not going to. Let's just use RBX as a counter then. So it's just already 0. So we can do something like top of our loop, make it look semi-nice. Then inside of the loop, we'll do a move RDI RBX, move RSI RAX, which we should probably do up here. And we can guarantee there's a good likelihood, and we can walk through it to show it that's true, that our SI and our DI are going to be the same values. The only ones that change after a system call are usually our CX and our AX. So all the other registers you don't really have to worry about, so we can just keep that there. Let's move RDI, RBX. We'll have to XOR out our AX because I think it's set to the new file descriptor if it's a success, or -1 if it's a failure. So RAX, move AL33. Yeah. Syscall. And then we'll increment RBX, compare RBX to 3, because we want to do standard input, which is 0, standard output, which is 1, and standard error, which is 2. And then if it's jump if not equal to top. And then from there, we could actually just put the rest of our shellcode again, because we're kind of back in our same place. Except for we'll need to refix this part, because now that's busted. So if we were to save RSI first and just push it onto the stack, which should work because RSP still points over here, but our shellcode is executing technically over here. I wonder if this actually would fit the 20. 8 character buffer. We can try. I don't think it will though. So push RSI can get rid of. Actually, I've got a better idea than that. So instead of doing RSI, what still points to technically our bin sh would be RSP. To RSP minus. So it's going to be right here. Minus 8, minus 2836, minus another 842, I think. Move RDX, RAX, which won't be 0, so we'll have to XOR that out. So RX, RAX, that should be fine, that should be fine, boom. So if we were to combine these, if the length of this is less than 28, then we should be golden, but I don't think it will be. It looks like a lot of stuff. Especially this part. I should change that to a BL, which is going to be just comparing the lowest bits. The lowest bit to make sure it's there. But if it's RBX, it'll compare it to 64 bits, which will be a lot of zeros in the 3. In the hex version, I guess. Shellcode is not defined because I renamed it. Step 1. That's defined. 48. Not even close. I don't really see much we could do to actually decrement this. We might be able to. We might have been able to change this up a little bit, but overall, we're kind of stuck in that realm. So now we need to actually find a way to be able to get all of the shellcode onto the stack. Or into kind of execution, I guess. And what we'll do is call this step. This should actually be step 1. Because this will happen before step 2. Anyways. So my preferred method to kind of any shellcode is that a lot of times there's going to be stuff that will limit you on what shellcode you use. Maybe there's certain bytes that you can't use. Maybe there's some kind of XOR operation being done that limits you. The kind of preferred method I go with is to always just call read call read, and this allows you to read in more bytes of whatever you want. You can read in as much as you want, so you're not limited in a certain facet. So we're still going to need our file descriptor to read. Move that to our DI. X. Actually, let's do this. Exchange RDI RAX. That should save us bytes. And RDI should be 0 because that's what we moved into earlier. If we do that, now we are left with the buffer we want to save it to. RSI currently points to our buffer right here, which I'm fine with. And RDX, which is the size we want, we'll need to read in enough to kind of run past where we're currently executing shellcode so we can figure out what we're doing. And we'll do a move DL. Let's go just 100. That should be enough. And then we can do a. We check this. I think it's 1. No, it should be 0. Yeah, 0, which RX should point to if we remember from RDI, the swap. So that should be all we need to actually send in a second stage payload, which will be right here. Now, if we think to this, we'll need to kind of think to the second stage. Once we get execution back, our DI will hold our file descriptor that we want to move to RSI. Our BX should still be 0, so we should be good with that. RX, we're going to 0 it out, so that should be fine. That should be good. Now, LEA RDI RSP minus 42. That should still be fine if we send in bin sh on our second read. No. Yeah, because we're reading into RSI, which is still going to be right here. And then, well, actually, if we did an exchange right here, we wouldn't even need to. Actually, yeah. I think it'd just be easier if we leave it this way for now. Move RDX RAX, RSI RAX, AL59 Cisco. So if we get this correct, so that should get us, this should all still be fine to leave the same. It should hit this shellcode. We're going to do a p.sendline of binsh plus probably at least, I'm just going to say 28 nops to say that we overflow our entire shellcode buffer, the original one. 28 plus our shellcode 2, which I'm going to rename to step 2 once I get there. I think that should work. So we just copy that there. Step 2. Don't really need that print anymore, but we can try it out. Go down here, make sure we're continued. Oh, P is not defined. Missed one. What did I do wrong? Seg fault. Looks like Step 1 should be the correct length, I believe. $15, yeah, that should work. I don't think I changed anything else. That should hit the right breakpoint. Oh wait, no, it definitely went past her. Didn't hit our breakpoint at all for some reason. That is the correct address, but definitely went on the stack. Just our 2B, which should be 2B, that's 59. I think. No. 32 plus E11 be 43. What is it running 43 for? Maybe this isn't on the stack. Oh, and I killed it. Whoops. Maybe it just died earlier. It just didn't want to go on living. I don't know. So we'll attach there. We'll make sure the set follow fork is going. Our breakpoint should be good. I believe this looks right. There we go. So that was weird. Maybe GDB just kind of lost hope when it tried to connect to the binsh, which it sometimes does, but no big deal. Jump back, hit the first nop sled, read in new characters, which it read in 5. No, that was to get the new file descriptor. So our current file descriptor is 4. Move then to RDI, move DL64. Yeah, because we're reading now. Okay. Ooh. I don't think we read in enough. We read in 4C. But as we can see, we stepped from F6, we're at F8, and we're already at the move. I move right here, so we missed this one. So we need to put in a little bit more nops. Which that doesn't really make sense to me, but no big deal. Interesting. We'll just go with 32. Well, we'll just go 40 just to be safe. Reattach. Step through. First Cisco, read. There we go. So here's our nops. First Cisco this is just going to start copying it. We're going to have to do that 2 times, 3 times. And now we come down to our binsh, which this should point to binsh, but it doesn't. Maybe that's why it failed the first time. RSI did not continue to point to where I thought it was going to. Wait, that's not RSI. This is RSI. Why is that off by? So it looks like my RSP is off by 7 characters. 6 characters. So close. I think the next attempt we should get it. But yeah, this is just kind of a lot of, if you don't know what's to do, you kind of just keep trying stuff until it works. Whoa. Oh, I thought I missed it or something. There we go, bin sh. RSI 0, our DX is 0, and then we have 59 right there. And if we just detach, and we can do ls. Oh no, I was really hoping that would work. But for some reason, if we look back over here, we can see that it's actually over here. So now we have to figure out why that didn't work. And I was really expecting it to. My first assumption would be that the copies didn't work correctly. If we check, hit 7. Wait, that was not right at all. RSI, maybe that was right. Man, 2. Yeah, old to new. Okay. So that was right. Increment RBX. Go through it again. RSI, our DI is 1 this time. 21, which should be 33. Because that was the system call we were doing, is 33. Do a step. Get 7, which means it should have worked correctly. Step again, 7. Move RSI, RAX. Move AL39. That one definitely failed. Why is RDI off again? This time by 5 characters. That's interesting. I wonder if... We'll go back to attach. I think it might be something on the lines of right here. We'll have to do a... just something like a raw underscore input to pause the program until we're actually ready to send in this extra send line. Or we could do something like get rid of that. So now it's not attached to the parent process. Do import time. So since we're not actually waiting for it to send in, I think it might be sending in too fast for the buffer and it's reading in some of this before it should. So time.sleep will go 0.2. Oh, and we killed it that time. Interesting. So probably have to wait for it to set up the port again. In the meantime, see if we actually did anything wrong, because I don't think so. This all looks correct. Instead of sleep, I'll do a p.interactive. That way it kind of works with the GDB. Detach from that. Yeah. Riveting exploitation techniques right here, as you can see. And it's already been almost an hour. This is taking longer of your guys' time than I was hoping for. Sorry about that. But sooner or later, I'll have to kill that.
It's all a part of the experience.
It's not killing any of the A.outs. For some reason, it still thinks it's working. Kill, tech 9. Maybe it is running still. That's why they won't create a new one. Hope that killed all the children. Okay, did. Doesn't look like we have that lingering SH one running either. To Ada out. So yeah, so if anyone knows how to force the port to realize that it's alive, because if we do netstat dash we can see that it's not actually listening anymore. Just for some reason it takes like a hot minute to realize that it's dead or available. What's this? What is... Maybe GDB? Still holding on to it or something? For some reason there's a Python instance living. That could definitely be holding it on. I don't know where that was at. Oh, I just... There we go. So I can connect to it again with GDB. Attach to that. Set fork mode. Set the breakpoint. And we'll do a little testing to see where we might be going wrong. So here it should just hang because now we have the kind of input waiting. So we just control C that first one. It'll read in the second one correctly this time, hopefully. Do that 3 times. Come down here, bin sh. Can't do that. If we just want to go and reattach to that one. Really? So yeah, this it should have connected back to us. But for some reason, maybe GDB, when GDB grabbed onto it, it killed it. So if we were to set the fork mode to parent, so this time GDB won't grab onto it, and kill this. That's weird. Opened up down here and sent in an LS. Is it this LS? Nope, the old LS. Or something. What did I do wrong? We'll have to consult the mighty text of the pre-exploit. So we can see I kind of was going with the same approach. 36, jump RSP, shellcode 1. I think in shellcode 1 is another jump. Jump back to shellcode, which is the first. Move, that looks the same. I copied it right here first. But that shouldn't matter too much where we copy it. No, I didn't. What was I moving DIL2 for? I was copying standard error that time. That shouldn't... maybe that is the problem. Maybe we can't... Since I'm copying standard error to... Our standard in, it's not correctly attaching it later on, because everything else, that's just saving it, reads it in anew, does it 3 times, 33, and syscalcs. Everything else looks right. Maybe it was just this part. So if we exchange that, we'll need to sort out RAX again. Let's just go into it blind, because that's always the best method. Didn't work. But if we check back here, why aren't you working? So let's set back to child, and it died. Maybe it didn't die. Maybe that was just the SH. Maybe it's still live right here, technically. Oh, it's just attach. Oh, it's definitely dead now. Yeah. There's an SH running, which it was hoping would be connected back to us, but it is not. Is any Python living? Doesn't look like it. So if we run it, hopefully one more time, this will give it to us. Okay. So we should hit a breakpoint. Jump back. Oh, since our shellcode changed, our jump needs to be more precise, maybe. Maybe not. 2. Yeah, that shall still work, because I didn't have anything else in before it besides just this move RDI versus EDI, which isn't a big deal. Move 20, so we get 5, which means our current is at 4. Put in RDI. Get rid of RAX, move DL64, read in our new shellcode. I controlled C the wrong one. Shellcode, Control C, NAPS, RSI to RDI, which is our current socket, or file descriptor, I guess. Move RDI, RBX, which should be 0. Get rid of RX, which should copy that. Go through it 2 more times, which since RX is equaling 5 means it should be doing it correctly. Increment. Should it be... Wait, why are we... I think... Now that seems right. I thought maybe that was our problem, but I don't think it is. No, that should still be right. Oh, yeah. I was thinking that this is 1 more than last time, but I was thinking maybe it should be 2 because we copied the standard error to 5 earlier, or 4 earlier, but it's not going to because our current file descriptor is based off the parent's connection, which we didn't create that copy on the parent, we created in the child, so it's going to be slightly different compared to them. So get rid of REX, move RDI, bin SH, RDX 0, RSI 0, AL3B. RSI, RDX, and a syscall. So it's definitely hitting the breakpoint. If we delete it, maybe continue. But it's opening up down there, which is not what we wanted. So that means it's not copying it correctly. And I'm not quite attached. I think I just botched that one. Kill that. If we look back at my previous one again, we can check this loop. I was putting R9 RSI, which would be the bin SH. Put RDX 0, which will be our RBX. Sort out RAX. Moved RDI R10, which was me saving our previous buffer right here. Or not buffer, file descriptor. Move RDI R10, move RSI RDX. RSI is going to be the wait, why am I... So if we look at the man of dupe 2, the old file descriptor versus the new file descriptor, and I am putting the RSI, the old one. Maybe I just have it backwards, and I just misunderstood what the old versus new meant. Maybe it wants the old file descriptor to be the one you want to put the new one into. So in this case, we would put 0, 1, and 2 into the old one. So if that's the case, I just need to swap these around a little bit. Let's put that to RSI, this to RDI, and try it hopefully one last time. Continue that. Put our breakpoint back in because I think I deleted it. Oh, yep. Put our next read in. Copy it once, copy it twice. So this looks more familiar, I think. But based on that documentation, I was a little confused, and that's my bad. So we'll just reattach that. And
Did you mean to do move RDI RDI or move
did I do
RDI
move
RSI?
RDI?
Yeah.
Then I did not. You're right. RDI already has what it needs. Man, I am presenter of the year today. Step through this. Got so much confidence that it worked. There we go. Look at that. First try.
Hey.
So, as a bad presenter, I forgot my own methods. And the correct way is to have the... See, that was just my bad because the man page... I misunderstood what the dupe 2 was doing. I guess I probably should have read a little bit further, but... Yeah, now that you guys have watched me fail for so long at that part, though, you'll never forget that the 0, 1, and 2 go in the second argument. So I know it's been pretty much over an hour now. I'll leave it up to you guys if you want me to keep going or if we should just save the medium and hard for possibly the future because... Yeah, because I just took a little bit longer than I thought. I think the medium might take 15 minutes, but the hard could take a little bit longer than that. So I'll leave it up to you guys quick.
We could just do the medium, and then you could save the hard.
Yeah. I also had a question, Logan. So like going back to that man page, so I know like in 32-bit how it would be from right to left. So wouldn't it make sense that RDI would be new FD and then our SI would then be old FD?
Well, we're not in 32, we're in 64-bit, so...
I know, yeah,
Old
but I don't
FD,
know
or
if like
the
it
first...
still goes right to left.
It's not really right... When it's on the stack, it goes right to left, but first it goes RDI or SI.
Well, when it's on the stack, it still goes left to right, but you push it right to left because that's how
Right,
the stack.
yeah, so that's what I
So
was
it's not
saying.
the order of the thing that's changing. It's the fact that you're using a stack.
Yeah. I was just thinking, I don't know, maybe it was right to left. I don't know.
Yeah, and you were thinking wrong.
Yeah.
Okay, so
Just kidding.
on to the medium. Let's p-kill all A.outs. See if there's anything running. Can close the easy. GDB, I think I might have killed GDB. That's a shame. But we can start A.out again, and this time I'll put a 1, so exec VE will be blocked. So that causes a little problems with our shellcode because we were running exec VE to get our shell at the end, right? So a easy bypass, or not easy, but yeah, I'll call it an easy bypass, is to actually know what kind of system calls you're working for, or working with. So if we were to just do exec VE, or control F exec VE, we can see that we have this one, but if we look, we also have a second one. There we go, which is going to be exec VE at. So what this pretty much does is just takes a directory file descriptor and then uses that as an offset to see what kind of file you want to run, and then pretty much the other arguments are all the same. But since we don't have a directory file descriptor, if we just put 0 in there and just put binsh still, it'll work the exact same as just pretty much a regular exec.ve. Don't quote me on that. So if we open up live again, we just need to change this very slightly to have 322 into AX because AL only goes up to 255. Move this into RSI. This will be our DX still. And this won't be RCX because RCX is a special register. This will be R10. And we can copy this because now we're also going to use R8, I believe. RDI, SI, DX, CX, R10, and then 8. Yep, R8 and then RA9 is the next one, but we don't really care about R9. So, if I look at this correctly, we're also going to need to move this into RDI, I guess. Make sure RDI is 0. I believe that looks correct. So we'll just connect again quick so we can walk through it to make sure everything looks hunky-dory compared to last time. Break. Set the follow, and we'll attach to this one. Hit our jump, first syscall, our second read. Go down, go through this 3 times. Get ready for our system call, just check everything. Our DI should be 0, our SI plus binsh, DX 0, our 10 0, our 8 is 0. Delete that, continue, and if we check, we can actually see that we get some kind of input back. And you're probably wondering, like, what's this bad system call? And that's actually the Seccomp filter continuing down. So what usually happens when you run a binary is that if you do something like strace of ls, it's actually going to use a bunch, or not really a bunch, but exec.ve at least once, I think. I just gotta find it. I think that's strace running, not the actual exec.ve, but somewhere exec.ve gets called, and that kind of just kills the process itself. So if you were actually good at what you're doing, unlike me, and program the binary to send interact with the user better, so maybe if you're able to tab complete, you could get something. So instead, we might have to guess to see what's actually in our directory. So if we did something like A star, we can see A.out's not found. So if we did B star, B's not found, all the way up to C star, D star, E star, F star, we can see flag.txt. So you could either do something like some kind of bash magic to read flag.txt, which I thought for sure I had one, but for some reason it's not being sent through. Otherwise, we'll just have to create new shellcode to actually open up the file and send it back to us. And if you're curious to what the shell was, or not the shell, the command, so we still have access to echo, so echo like ls, we're able to echo stuff. So if you do echo with, not that, but if you put tick marks around it, it should print out the flag. Or if you just did this around that, it should come up with that. But if we were to try it here, it just gives back nothing, and I can't really figure out why. Maybe it's because we don't have like an active PTY instance or something, but I'm not really sure. So instead we'll just have to do some more shellcoding to, instead of running binsh, actually send us the file, because we could maybe replace this with cat the flag, but I didn't actually try to do that for you, but it just says bad system call again, so we actually need to do a custom read and write shellcode for it. So we still need this part right here, but this part is kind of junk to us now. I'm going to kind of want to leave it, but it's not really needed. So we need to figure out what our system calls we want to do. So first we need to actually open the file. Instead of reading from the file and saving it in a buffer and then writing back to us, I'm going to do what is called a programmer move and use a system called send file. And all it takes is the out file descriptor and in file descriptor and your offset and count, and it'll send all of those bytes straight to us. So we'll XOR RAX with RAX, move that into our DX, move that into our SI, so we have 0 flags and 0 permissions on the when we open it. I think that just defaults to read or something. I'm not really sure how that works, but it works. We'll need to LEA RDI, go RSP minus, is it 48? That's going to be sure hope it's 48. And here we'll put flag.txt. 2, 4, 6, 8. So let's get rid of one of these guys. So now our DI points to our flag. Now we can just do a move AL3. Though I just looked at it. 2. The third system call. To syscall. Syscall. So now our file should be open and our AX should point to it. So we'll need to move that into our SI 40 out. Yep. So our SI will be our file we read from. SI RAX. Move RDI whatever our previous one was, and I don't think we ever saved it. So we'll have to do a RDI was here, so we'll just move that into R10 just to save it, because R10 is also going to be a safe register. We could have pushed it on the stack, but that kind of just messes up our RSP value, and I don't want to deal with that too much. And our shellcode is also on the stack, so there's a chance we end up overwriting our stack, and in that case, you could just subtract or add RSP to get RSP somewhere else, but it's not worth the hassle when you have registers available. So we'll need our DX to be 0 because that's the offset, which it should still be. And then our 10 will be the count, which in this case our 10 will be greater. Won't be enough though. We'll just move our 10 word. Oh, we'll put the byte. Ooh. I want to use L, and this is going to take the lower 8 bits, like AL or something. I'm pretty sure. Maybe it's B. Pretty sure it's L. But I don't think Pro Tools accepts this for some reason. Move AL40, syscall. Let me just check. And then I'm just going to comp this out because I don't want it to crash our server. Or not the server, but just the instance. And as you can see,
The
I've crashed it
syscall
7 times.
The syscall on the last line is misspelled.
Good catch. Sysackle. So yeah, doesn't like the move. Maybe it was. Pretty sure it's L though. Okay, it is B. My bad. So as you can see, you should need to. It helps when you actually know what kind of stuff you're working with. Why didn't that break? Oh, I deleted the breakpoint. Darn it. Yes, where are we? So we just... Oh no. Oh, perfect. Ah, if I didn't do that, that would almost been perfect. Because we were just right after our first read, and this is waiting for our control C to send in more data. But I messed it up, so I'll just try it again. So first read, because that's still the same. Hit our first snop sled, check to make sure flag.txt is there, that looks good. We'll do this 3 times, which it's not actually needed anymore. Could have taken that out. And then here we'll check our open, which is 200 RDI, which is flag. See that it opened, and that's a new file descriptor now. Then RSI becomes 8, RDI becomes R10. Yep, R10 becomes 64 hex, which is 100. AL becomes 40, and our Cisco becomes the print of flick. And that's the medium, and now it's going to crash, which a good exploit dev would have put not air handling, but just would have killed it, so it wouldn't have broken this bad. But yeah, that was the easy and the medium one. I guess one thing I wanted to show you that I totally forgot about earlier is the ability to check, an easy way to check to see what a Seccomp is actually being ran instead of either. It's like in case you're not actually given a printout saying what's happening, like this program is so generously given to you. So there's some tools called Seccomp tools. Which now that I think about it, it's probably going to just get all. Whoa! I think I just restarted my VM on accident. Well, that's a shame. Okay. Hopefully that doesn't cause any problems. Well, at least we know that the 8-out processes are dead. Temple, shellcode. So there's tools called Seccomp tools, and then you can just do dump 8-out, and it'll say difficulty 2. And now when we actually connect to it, okay, localhost 8089, because it doesn't actually set the Seccomp tools until it's ran, or until it forks. We can see that we have this Seccomp, or this pretty little, I don't want to call it graph, but decompilation. There we go. So it'll check for the system number, or syscall number, put it into A. If A is not equal to execve, it goes to the next one of your check. If it's not equal to execve add, it goes to the next one. If it's not that, it goes to the next one. And if it's not that, it goes here. If it is any of these, it goes to kill or returns kill. So this is considered a blacklist approach, so you're not allowed to run any of these. Whereas if we were to do, yeah, oh, I gotta kill that. Think it might take a little second now because I left that open on accident before I killed it. If we were to check out the 1337 one, because this one and the protection one looks pretty much the same, except for this part will be different. There'll be another part above. So this will be the only one that's in there, I guess, but it's still kind of a blacklist approach. Come on. Come on, tools. You're making me look like a fool in front of everyone.
Just reboot again.
Honestly, that was actually pretty quick. I'd prefer not to, though. If I just ran it from somewhere else. I don't think that was the actual reason why. I don't have a better answer.
That made no sense.
Alright, so I did a 1 just to show you what the 1 looks like, and .96. Oops. And here we can actually see, compared to this one, where we also have a check for the arch is equal to x86 64. That can maybe be a hint to this kind of exploit or bypass, but all it does is check for execve and then kills or allows. So cross fingers. We just gotta try a new terminal. Darn it! That just I was not expecting it to work right here. That was just prime
the
time.
luckiest thing. Yeah.
Alright, let's set a. I don't know. Just so I'm gonna set a timer, but I don't really know how to set a timer. If there's a, could set a watch, I guess, but. So I'll show you the 1337 one, just show you the difference between a whitelist and a blacklist, because that one's going to be a whitelist approach. Separate. 1337. Only you know what you're capable of. Do I need to send? Yep, I sent in the data before. And here's the Seccomp filter for this one. So this will check to make sure the arch is the same. Then I'll check the syscall number, and if it's not equal to exit, so this is a whitelist, so it has to either be exit, open, write, dupe, dupe2, end protect, close, stat, kill, get process ID, and get parent process ID and get process ID. So what this approach is doing is saying that you don't actually have the ability to read in data, which, now that I think about it, I think it still only reads in 56 characters, so it's definitely not going to be able to be possible. Unless you can come up with some crazy shellcode to send a flag without being able to read it. Let me just do a quick check. Nope, it reads in more bytes. This one will read in 0xFA, so 250? Yeah. So you have 250 bytes to figure out how to get your flag without reading. And I think this one's possible, but it all depends on parent to child relationship permissions. But that'd just be spoilers for a pretty cool write-up if it works. Or you could just go online and find the challenge I blatantly stole this from. But yeah, any questions or any ideas on what maybe the bypass for this one is? Because we can't open a file and we can't execute anything. Okay. Thanks for coming in and learning about some pwn.